So today we're going to focus on the extreme value theorem. And the extreme value theorem is used to help us identify absolute extrema of a function. So in the previous unit, we really investigated how to locate the relative extrema, the relative max and min, using our first derivative and even our second derivative. In pre-calculus, we talked about the difference between the relative and the absolute extrema. So let's first identify that, okay? What's the difference between the two? So the relative extrema are points on a graph of a function where the function changes from increasing to decreasing or vice versa. Now, the absolute extrema are the highest and lowest defined point on a graph. So all absolute extrema are relative extrema, but not all relative extrema are absolute extrema. Okay, so let's look at this first set of pictures. Below are the graphs of f and g. Answer the questions about these two functions. So let's look at the graph of f of x. Identify the coordinates of the relative extrema of f. So we could definitely say the relative mins, okay, which means that they go from decreasing to increasing, are at -3, 0, and 2, -6. And the relative max, which goes from increasing to decreasing, is at -1, 3. Okay? Now, on the domain of f, what are the coordinates of the absolute extrema? So what's the highest defined point and what's the lowest defined point? Well, there's no relative max. All right, and that's because there's no highest defined point. This point goes on forever. So there is no absolute max. But there is an absolute min. Our absolute min is located at 2, -6. And if they asked you for the min value, it would be -6. All right, I'd like you to answer those two questions for the graph of g of x. So if we were to identify the relative extrema, we would identify that we have relative mins at -3, -4, and 3, 2. Okay? That's where we went from decreasing to increasing. We would have only one relative max at -1, 4. These endpoints are not relative maxes because they do not change from increasing to decreasing intervals. They are just endpoints. Now for the absolute extrema, we know our absolute min is at -3, 4, -4. The absolute max can occur at the endpoint, and that is at 6, 5. That is the highest defined point of the graph. So that's the major difference between relative extrema and absolute, okay? The absolute extrema do not have to occur at the relative. Absolute extrema do not have to occur at the relative extrema, okay? The key thing is they can occur at endpoints. While relative extrema cannot. Okay? Does anybody have any questions about that? I hope not. If you do, write them down for class. All right? So let's look at another example. Let's look at the graph of f of x. On the interval from -2 to 3, what are the absolute extrema? Well, once again, we have an absolute min at 2, -6. Do we have an absolute max? Nope. No absolute max. It goes on forever, okay? Now, oh, let me take that back because now I see that they specifically told us a certain interval. So from -2, so this part of the graph, to 3, this part of the graph. So just those parts. So we essentially have endpoints here. Okay, so we do have an absolute max here with those endpoints. It occurs at -1, 3. And we have an absolute min here. Okay, it occurs at 2, -6. Now, let's expand our interval from -4 to 1. All right, so here we have -4 to 1. Okay, so what is our absolute max? Well, here we have endpoints, and the endpoint is actually our absolute max at -4, 4. Our other endpoint is our absolute min as well at 1, -3. So once again, absolute extrema can be at the endpoints. Okay, now in the first part, the absolute extrema occurred at a relative max. Okay, but that's only because we enclosed and gave endpoints. Go ahead and answer the next two questions on the graph of g of x. So based on what we have seen here, what can we conclude? Well, we can conclude that there are three places that the absolute extrema could exist. We can conclude at endpoints of the interval. We can conclude where the first derivative equals 0, which means at a relative max or min, or where the first derivative is undefined. So, the theorem of EVT puts this all together, right? And the theorem says that if f of x is continuous on the closed interval of a to b, then f of x has at least one max and at least one absolute min on the closed interval. And once again, the interval has to be closed in order for this statement to be true. Okay, so how are we going to use EVT when asking about absolutes? Well, let's look at this example together. Consider the cubic function f of x is equal to -x to the third minus 6x squared minus 9x plus 2. Well, the first thing we need to look at is we can pretty much identify the shape of this graph. We have a cubic function with a negative leading coefficient. So if we remember, our end behavior will look something like this. That's what we expect it to look like. So the first thing they ask us is to determine the intervals where f is increasing and decreasing and justify your answer. So right away, when we see the terms increasing and decreasing, we should automatically be thinking, oh, this is in relation to the first derivative. So we need to find the first derivative. So the first derivative of f is equal to negative 3x squared minus 12x minus 9. Okay? And then we're going to do the first derivative test by setting it equal to 0. We're going to factor out negative 3, the GCF, and when we do that, we get negative 3 times x plus 3 times x plus 1, which means that our critical values are negative 3 and negative 1. All right, so then we're going to do our first derivative test. And when we plug in values, okay, we're going to get negative here, positive here, and negative here. So we know our increasing interval is from negative 3 to negative 1 because our first derivative is positive, okay? And we know our decreasing interval is from negative infinity to negative 3 and from negative 1 to positive infinity because our first derivative is greater than 0. I mean, less than 0. Sorry. All right. So the next question asks, determine the coordinates of the relative extrema. So we already found the relative extrema to be at negative 3 and negative 1. All right, so we need to determine the coordinates. So when we plug in negative 3 to the original problem, okay, when we plug in negative 3 to the original problem, we get 2. And when we plug in negative 1, we get 6. Now, because we're going from decreasing to increasing at x equals negative 3, so decreasing to increasing, we know this is the relative min, all right? And because we're going from increasing to decreasing, we know this is the relative max. And we can say because the first derivative changes from negative to positive, and here, because the first derivative changes from positive to negative. All right, so pictured below is the graph of the function f on the closed interval. And it asks us to identify the absolute maximum of f on the closed interval negative 1 to 4, negative 1 to negative 4. So we know it stops right here. This is our part of interest for this first question. So the absolute maximum. Well, in this case, it happens twice at negative 4, negative 6, and negative 1, 6. So it happens at both endpoints. The absolute minimum based in this interval is negative 3, 2, which is one of our relative minimums. Okay? Now, if we expanded our interval to negative 4, 1, so that's our entire graph now. That's our entire graph. Okay? Where would our absolute max happen? Well, it would still happen in exactly the same places. It would be at negative 4, 6, and at negative 1, 6. Now, interestingly enough, when we expanded our interval, the relative max occurs at the absolute max occurs at an endpoint and at a relative max. And then the absolute minimum in this case would occur at the endpoint of 1, negative 14. That's not a relative because it's an endpoint. It just doesn't change from increasing to decreasing or decreasing to increasing. So this is all and great if you're given the graph corresponding to your given function. But what happens when you're just given the equation and you don't have your calculator? So use the extreme value theorem to locate the absolute extrema of the function on the given closed interval. Your algebraic results should concur with the graphical conclusions we had from the previous page. So we already did the first derivative test, okay? We already did the first derivative on the previous page, so I'm not going to do that again, but I'm going to remind us that we found our relative max on our first page, or on our previous page, to be negative 1, 6, and we found our relative min to be negative 3, 2. Now, when they give you the endpoints, you need to find their numerical value. So you need to find f of negative 4, and you need to find f of negative 1. When you find f of negative 4, you get 6. When you find f of negative 1, you get 6, which we actually already knew. And now we have to talk about our relatives. Well, our relative max was already included here. And our relative min, I just added. And this is an endpoint, as well as this. Okay? So what you can do now is identify that the absolute max is at negative 4, 6, and negative 1, 6. And the absolute min is at negative 3, 2. Okay? So let's do it with the problem in which we don't have the graph and we have nothing to compare to. So h of x is equal to 3x plus 2 times all over x plus 3. And you have to state specifically why EVT is or is not applicable on the given interval. Now, remember, in order for EVT to be applicable, all right, it means that it is differentiable throughout that entire interval. And that's really important. EVT is applicable if and only if it is differentiable within the interval. And what's important here is we have to remember that part of the definition of differentiability is that it is continuous within the interval. So when we look at this first example, all right, we know that x cannot equal negative 3. That would make it a discontinuous function. And in this case, negative 3 falls into the interval. So right away, we can say EVT is not applicable because h of x is discontinuous at x equals negative 3, which falls within our given interval. Okay? When we look at the second example, okay, we recognize that because we have a radical, the domain tells us that x has to be greater than or equal to 3. All right? So in this case, we can say EVT is not applicable because h of x is only continuous for 3 to positive infinity, which is not within our given interval. All right, for our third one, okay, in this case, we know the rules of logarithmic functions, that our logarithmic number has to be greater than 0. So x has to be greater than negative 7. Oh, that falls into our interval. So we can say EVT is applicable because it is continuous for all values greater than -7, which is within the interval given to us. So what's really important is even before you try to use EVT, all right, you have to make sure that the function is continuous, okay? So let's look at our first example here. F of x is equal to x to the third minus -2x squared minus 3x minus 2. So the first thing you can automatically say is this is continuous for all real numbers. So right away, EVT is applicable. So we can use it to find the absolute extreme values. So the first thing you're going to do is you're going to find the critical points. And you're going to find that by doing the first derivative is equal to 3x squared minus 4x minus 3. You're going to set that equal to 0. And you're going to realize, this is not factorable. So if I can't factor it, I have to use the quadratic formula. Okay, and if I use the quadratic formula, I get x is equal to -535, and x is equal to 1.869. And do not forget, in AP Calculus, you always round to the third decimal place. Okay, so now we're going to do the first derivative test. So -0.535 and 1.869. Okay, so when I plug in a value into the first derivative, okay, between -0.535 and 1.869, so I'm going to do x equals 0, I'm going to get a negative value. When I plug in x equals 2, I'm going to get a positive value. And when I plug in x equals -1, I'm going to get a positive value. So if we find f of -0.535, we get -1.121. And we know that's going from increasing to decreasing, so that's a relative max. When we find f of 1.869, we find that to be -8.065, and that's a relative min because it goes from decreasing to increasing. But we also have to take into account our endpoints. So we have to find f of -1 and f of 3. And remember, you're plugging this into the original function. So if we find f of -1, we get -2. If we find f of 3, we get -2. So our absolute max, which is our highest defined point, all right, is at -0.535, -1.121. Okay? Our absolute min, sorry, I'm running out of room, occurs at 1.869 and -8.065. So interestingly enough here, our absolute max and our absolute min occur at our relative max and our relative min. All right, let's do the next one together. G of x is equal to sine squared x plus cosine x on the interval from pi over 2 to 2 pi. Okay, so we know that this is continuous because trig functions go on forever. All right, so we can say continuous on -infinity to +infinity. Okay, really important. So we're going to also rewrite this as sine x squared plus cosine x because that's going to remind us that we have to do the chain rule. So when we do that, we get 2 sine x cosine x minus sine x. We're going to set it equal to 0 and factor out sine x. And we get 2 cosine x minus 1. All right, so sine x equals 0, and 2 cosine x minus 1 equals 0. So cosine x equals 1/2. Now, what's really important here is that we look at our interval, okay? Because our interval will tell us what values we can include. Because we know that sine x equals 0 at 0 and pi. But 0 is not included because it's not in our interval that's given to us. All right, we know that cosine x equals 1/2 at x equals pi over, oh my gosh, pi over 3 and 2 pi over 3. All right, but pi over 3, not in the interval. So those are our two values. Okay, now, g of pi over 3, g of pi over 2, and g of 2 pi, which is our endpoints. So g of pi over 2 equals 1. G of 2 pi is equal to 1. G of pi is equal to -1. And g of pi over 3 is equal to 1.25. So right away, you can tell your absolute max, I'm sorry, this is 2 pi over 3, is at 2 pi over 3, 1.25. And your absolute min occurs at pi over 2, 1, and 2 pi, 1. Okay? So now, I would like you to do the next two on your own. Identify the absolute max and the absolute min. Remember, you need to make sure that EVT is even applicable. Okay, you need to make sure that EVT is even applicable. So remember, in this case, this is going to be rewritten as the third root of x plus 2 squared. Is it continuous always? Remember, in this case, you want to check that x squared minus 4 has to be greater than 0 because of the rules of logarithmic numbers. Good luck, everybody.